Okay, I am recording on my end, and I am yet to be recording on not my end. There we go. I'm sharing my screen, but I'm sharing the wrong screen. So 1 second. So I came into this meeting a little late and frantic because you don't see me. Why don't you see me? There I am. Okay, there I am. So hopefully now everybody sees my screen. Sees me and my screen. I will open the Zoom chat to verify this, and then let me open Discord. But I will hide the screen while I open Discord, just so you don't see anything. Everybody can see my screen? Well, now you can't. It's black. But now everybody can see my screen? Yeah?
Yes.
Yes? Good. And let me get this all going here. Am I sharing the right thing? Sorry, guys. A little bit of a mess here, but this is what I meant to share. There we go. And now you can see me. There we go. Now I think we're working. So, yeah, my plan is to do B. 1B. Let me open that up. Or is it A? No, it's B. This one. I could do both of them. It's fine. Like, it doesn't matter. Like, whatever you want, whatever you'd like for me to do, I'm happy to do. But I think it's B is the one that I'm starting with here. So let's give that a shot. I will have the chat open. Feel free to unmute anytime, and let's get the party going. So, and I'm recording, and I am recording on Zoom in a second. Record to the cloud.
Recording in progress.
Okay. Hello, everybody. Welcome to the MTH314 tutorial. So 314, which is the discrete math tutorial. So I am a fourth-year engineer. I do tutorials for the math department every once in a while. I have notes on this course. So I took this course a little while ago. There's notes on my website. So my website, which is www.tutor.ca/notes. Okay, you can go here. I have notes on this course. When I took this course, there was a different professor, so it's a little different. But I also have notes for just straight from the textbook, so you can just go through that as well. When I did this course, there were no proofs, so that's just very different. But anyways, I can still do it. So yeah, this video will be posted on my YouTube channel, which is just my name. Okay, so my YouTube channel, which is just Adam Sava. And you can find that there, and then the PDF will also be posted there. Maybe Muse will post it as well. I don't know. Zoom chat will be open. Feel free to unmute or just comment or just say something in the meeting chat, whatever you'd like. Otherwise, I think let's just get into it. I'll start with, I'll just do it in order. If anybody has any questions or anything that they'd like to note, then please feel free to unmute and all that. And if there's any connection issues, or you can't see me, or you can't see the screen, or you can't see different things, then or something's wrong, just tell me. So first question says construct the truth table for this. So to do that, we need to have an understanding of what truth tables are and how implications work. So you always start with all of your variables on the left-hand side here with all the different values, right? So it's like 111, 110, 101. It's like your binary values here, true and false. And so there's all the possible combinations. And we just kind of use that to think about all the possible values that this statement can have. So you just start constructing it piece by piece. So first thing to construct in this is P and Q, right? Because that's the first kind of component of this. You can start with R, not R if you want, but you can do that. So P or Q. So P or Q is, let me do a proper line. a connection between these logical statements, and it's just an OR gate. So P or Q, we're just focusing on these two rows here. Right? So P or Q would be true, 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 and false. False, right? Because it's OR. So this little logical connective, that's a V, is like an OR. Because I think of it like the union, right? So union is like that, which is OR. And the next thing is not R. Right? So not R is just the opposite of R. Right? It's just the opposite of R. So we take all our values for R and we just invert them. R is going true, false, true, false, true, false, true, false. So it's going to be false, true, false, true, false, true. False, true, false, true, false, true, false, true. And now we fully put together the implication. Right? P or Q implies not R. So the implication is just connecting, it's again a logical connective, right, between these two statements like this. And the idea is that this statement is true. It's true that A implies B if whenever A is true, then B is also true, as in A implies B. But it's a little bit more than that, right? Because in English, if I say, if it's raining, then the floor is wet, right? I usually, I'm assuming that the hypothesis there, the first thing I'm saying, if it's raining, I'm saying, let's say it's true, right? I'm not pretending like that is false. I'm saying, let's say it's raining, then what happens after that? But in this logic theory here, it doesn't have to be true. So we just say it defaults, the whole thing defaults to true if the thing you're starting with is false. So what do I mean by that? I basically am just saying that the last two rows here are true just by default. Like they're just vacuously true. And the reason for that is that right here we get two falses. The thing at the start of the implication, right, is false, and so the whole statement just automatically results in true. That's often a point of confusion, so I understand if that's something you want to talk about, but that's something just kind of to memorize about how we've defined these logical connectives here. We've kind of just defined it to work like that. Anyways, from there, we just say, okay, well, we ask ourselves, if this is true, then this is true, and then that makes the whole thing true. So, for example, this would be false here, right? Because the start is true, but the result is false. So the implication that this implies this is not true just in that row. Here it's true, right? Because true implies true. Here it's false. Here it's true. Here it's false. Here it's true. And then it's just true, true after that. But the reason for the last two truths is different than the reason for the truths before it, right? The truths before it is because P or Q implies not R. That worked out. And there we go. That's our first question. We constructed the truth table for P or Q implies not R. If there's any questions about this, feel free to ask. Otherwise, I will just move on.
What type of gate would the implies be? So like in CO328, what type of gate would it be?
Yeah, I get your question. So we know that P implies Q. It's not just a simple answer, right? So it's like P implies Q is logically equivalent to what is it logically? It's a P and not what is it? P, not P and Q. I'm getting it backwards. Let me remind myself. Not P or Q. That's what I'm trying to say. Not P or Q. So not P or Q. Not P or Q. So you would do this. It's like a not gate and an or gate together is what it is, right? Essentially that, right? That's basically it. Does that make sense?
Yes.
Sounds good. I just want to make sure what I wrote is actually right. Anyways, so not P or Q. Perfect. Great. Just verifying that's right. Yeah, because otherwise you have like your and not and or gates and all this stuff and XOR and all this, which is exactly what you expected it from digital logic, right? And then this is just slightly different. We have more connective, so we have more words, and this is more fundamental. But it is Boolean in nature, right? Because it's just true or false. So we have a lot of parallels there. Okay, I will continue unless I have any questions. I usually stream from home. Today's a at school day, so hopefully the quality is keeping up here. It's not as good as from my at home setup, but it is what it is. Okay, show that this statement is equivalent to that. Do not use a truth table. So one way we could do this is we could set up the truth table for both of them and then just show that the final column, their truth values, are the same. But that's tedious and it doesn't really show like deeper connection here, right? So instead, we'd like to just use some logical rules to kind of connect this with this to kind of go from here to here. So when I'm looking at this, I see like to myself here, like there's a few rules that I can use. First of all, what I'm trying to get to has an or connective. What I have has an and connective. Okay, I need to use De Morgan's. That's my first thought. Okay, I need to use De Morgan's because De Morgan's, which tells us, there's a few ways of saying this, right? But it's like P or Q, and you take the inverse of this, like not of this, is logically equivalent to not P and not Q, right? So you see how it switches the operation there. Like I could do that now, I can do that later, it doesn't really matter, but I will do that now essentially. And what I'll do is I'll basically do this in reverse. So I'm starting with this, right? And then I'm going to go to this. So what I have is, it's a different color. So this right here is basically what I have right there. Now, I don't have a not on the P, but what you can do instead is you can say that, the thing we start with here, like I'll just call this, like just so I don't have to rewrite it, I'll just call this A. So A is logically equivalent to not P or and not Q. So now the point of doing that is just that it's a little bit more in this form. You don't have to do it if you don't want to. And what I'm saying is, according to De Morgan's, that this is going to be logically equivalent to, I can kind of like factor out the not, right? I can factor out the not, and it becomes not P or Q, right? I guess I just meant this to be A. I just meant that to be A. So what I'm saying is that I can take that first statement, right, which is P and not Q implies R, and I can say that this is logically equivalent to not P or Q implies R. So that's really my first.
How did the not P become not P?
Well, it's like the not. It's not that the not P. It's the P from here. The P from our actual first statement. Yeah. I highlighted it incorrectly here. This should be like that is that. Does that make more sense?
Gotcha. Yep. Thanks.
Yeah. So now we are going to continue with this. So I need to get this into a form that I have more rules that I can apply. First thing that I'm going to apply here, this was essentially the first rule that I applied, which was De Morgan's law, right? De Morgan's law here. The second rule that I'm going to apply is the rule for implications, right? So P implies R is just like A implies B, is logically equivalent to it's the second time I'm forgetting this. Not A, I wrote it up here. Not A or B, like this, right? So this is our second rule that we're applying. So we will continue from here. I want to color code it a little bit better, just so it's a little easier to read. So like this was our rule that we applied. And this was also a rule that we applied. So now I'm going to continue from here. I'm going to continue from here. ... logically equivalent to. Okay, so that's logically equivalent to not of the beginning bit or the second bit. So the not of the first bit is just not P or Q. right? That's the not of this. That's the inverse of this. Or R. Okay, well, this is good. Oh, and I guess, to be clear, there's brackets around this, right? Just to keep the order of operations here set, because there were brackets around this. But now we can use our associative law to say that this is the same thing as negative P or Q or R. Right? So this rule right here, what I just applied right here, is associative law. Associativity. Right? Okay, good. Now I'm just going to apply number 2 again, but the opposite direction. Right? Keep in mind where we're trying to head. I guess that's what I should remind you here. Right? Keep in mind where we're trying to go. We're trying to get to P implies Q or R. Right? So, if you wanted to spell this out a little bit more, right, you could say this is not P or Q or R, right? Because same rule, same as rule number 2 that I used here. Well, that's exactly what we have, right? That's what we have right here. So I can just do that. I can just say that this, again, just logically equivalent, according to rule number 2, to P implies Q or R. And this is again due to rule number 2. And we are done. So it's really like just to kind of spell out the steps a little bit more, right? First step, second step, third step, fourth step, and then finally fifth step. So you see how we went from the thing that we're trying to start with and the thing that we're trying to turn it into. Any questions here? We're done with this question. Okay, so let's just keep moving. So this next question has a bunch of, it's about argument forms, right? So, argument forms are basically ways that you can lay out statements to show that some other statement is true. And, in some order, not necessarily needing the order, but in some order. So I think what might be good for us is to first lay out what all of these valid forms are, right? So the moduses, and then the also the logical equivalences and the instantiation rules and stuff like this, right? So why don't I just write them out? You probably have a table of them, but I think it's good to just let's just talk about each one. Just if we talk about each one individually, it's probably going to help you remember them. I don't know what you're given on the test, but I'm assuming it's not a table of this. So the first one is called modus ponens, right? So modus ponens looks like this. We start with the fact that P implies Q. We assume this is true. Then we have the fact that P, right? So from this, we draw a little line like this, and we say that from this we can logically, if this is true and this is true, we can logically conclude that therefore Q, right? So if we know that if P happens, then Q happens. P happened, then Q must have happened, right? If it's if it's raining, if it's raining, then it's wet on the ground. It's raining, so it's wet on the ground.
Sir, sorry to interrupt you, but we actually do have all of them on a cheat sheet.
You have all of them. Okay, that's good.
Yeah, they're good.
So then we won't spend too much time. I'll just write them, but it's just good to know when to use what. I guess we can just go into the example then. If you have all of them, we can just go into doing this. But yeah, so all of them are essentially very simple logical forms, as simple as this one, right? As simple as this one. I mean, I did modus ponens. I may as well do the other one, and then we can do the example. The other modus tollens. Right, so modus tollens tells us that if we know that P implies Q, we know that Q is not happening Therefore, we know that P didn't happen. And this is another logical form that we have that we can use. So yeah, let's I'm just mentioning those because those were specifically named here. These kind of questions are a little messy. It's not a super clean way of doing these, especially given how they're presented and how your teacher expects for them to be written. But it looks kind of like a mess, right? So the idea is that you assume all these premises to be true here, right? All of these beginnings of the argument. You assume all these premises to be true. And from there, you see if you can use their logical connectives, like you can connect them, to get this conclusion Q here. So you don't have to do it in order, right? You don't have to do it in order, right? So for example, starting with number 3 here, right? I like starting with the and, because that really tells you what's going on. W and R. Okay, therefore, W. Additionally, now we know W. W is a true statement, right? Because we know, not W, my bad. Not W, as in W did not happen, right? Additionally, right, we also, because of W and R, right, we know that R happened. Same statement, right? We know that these two. So we know W and we know R, right? Then we know not W and we know R. Then from 4, which is W or U, one of those two things happened. We know that one of those two things, I like to think of them like events, right? So like W is an event that happened or not. I mean, it's not really an event. It's like it's a truth value. So we know if it's true or false, but I like to phrase it just like an event, right? So W didn't happen. We know that for sure. R happened. We know next that W or U happened. Well, we know W didn't happen, right? We know this, not W, right? Which is a subsidiary of the statement 3 here. Therefore, right? Therefore, U must have happened. Just logically here, right? If we know either, event W or event U happened, event W didn't happen, therefore it must have been event U that happened. So we're getting a lot of values here. We know that W didn't happen, we know that R happened, we know that U happened. And this is just from those last two. Again, you don't have to do this in order. Right? The question. Yeah, not W is true, as in W didn't happen. Like phrasing it like an event, like W didn't happen. Okay, so let's continue going, right? We're trying to get Q. Q is the only thing in here, right? That's the only place Q is. So, if we could somehow prove that not P happened, well, then we could prove that. Well, we could make progress in that direction. But anyways, we can prove not P because we know that U implies not P. So according to 2, which is U implies not P, we know U happened. Therefore, we know not P. Just to kind of color code here a little bit, right? We know this U. Use a better color than this. Where's my undo? There's my undo. U, we know it from right there. That's how we know it, right? And then again, color coding here, right? How do we know not W? Well, we know not W from right there, right? And then, yeah. So from here, we know that not P, like from looking at it, we see that not P implies R and Q. Well, we know not P. We know not P is Q, right? So I'll start writing that. This is number 1. So we know not P implies R and Q. We know not P. Therefore, we know R and Q. Well, last step here. Since we know R and Q, basically, therefore, since R happened and Q happened, therefore Q. And we're done. We showed that Q happened, right? For 4, W or U is assumed to be true, but we know W is false because not W is true. Because of that fact, W being false, U must be true since U or W or U must be true. No, yes, I agree. Because of that fact, we know U must be true. Yeah, that's what I wrote. Exactly. I agree with you. So we know U is true. Therefore U. That's what I wrote right here. Yeah. If U is true, how is P false? Because of this right here. Because they gave us that as a statement. If U, then not P. So someone asked in the chat, if U is true, how is P false? Because of this statement right here. That's the answer. So it says you do not need to provide names. So, you could name each one here. Let's name it, whatever. Let's just name it just to make sure we understand everything here, right? So this first one, if I remember the names, so it's so this one here is specialization. Specialization. So these two here are specialization. Let me use a different color. Specialization. The next one, is there a name for the next one? Yes, there is a name for the next one. So the next one is elimination. The next one is modus ponens. Modus ponens. And this one is also modus ponens. And this one is with the and is specialization. Right, because we know R and Q. How do we know R and Q? It's not one of the things given to us. R and Q is not given to us here, but it logically follows from assuming all of those arguments are true. That R and Q must be true, therefore Q must be true, which is really our end goal here.
I had a question.
Go for it.
Sorry to
Go for it. No problem.
For example, you see how you got the not W? Are you allowed to use it multiple times in different arguments? See how you used it in 4, but imagine there was a 5. Were you allowed to use not W there?
Sure. Yeah. If you can somehow logically show that not W is true, that not W, then you can use it wherever because you know that's true.
So you could use any argument multiple times, right?
Yeah.
It's not a one time and it's done. Okay. Thank you.
I can't think of a time when it would be a one. Yeah. I according to my knowledge at the moment, no, there's no way that it would be just a one time there. This is why I like to start with the ands, because you right away you get some values. You're like, okay, now I know that R and I know that not W. Great, right? So it's good like that. Okay, so if there's any questions, please unmute or please ask in the chat. Otherwise, I will just continue. Take that as a no. So our next question is prove or disprove the following statements. This is the good stuff here. This is the good stuff. So, proofs are a very fun part of math. I don't know if you agree with me at this moment. Some of you might be shaking your head. But, they prove their own challenges. So let's give it a shot here. The next part, it says, prove or disprove the following statement. Clearly state your answer if it's true or false, as in if the statement is true or false. Now, if you're trying to prove something, right, this is a very powerful thing we have in math, which is we can prove statements to be true for all elements of a set. Now, certain things are easy to prove. Certain things are hard to prove. The first thing is to try to understand what you're trying to prove. And so we have statements that are in these forms with these quantifiers. Right? So it's upside down A, backwards E, and let's first break down what this is actually saying here. That's the first very important step here. So this is a statement. This is something we can prove to be true or false. Okay, so what it's saying is that let me move the chat back up just so I can see it. So what this is saying is that for all x values that are natural numbers, as in positive, so 1, 2, 3, to be clear here, right? N is 1, 2, 3, ... Okay, so x is any of those numbers. There is, associated with that x value, there is a y value such that y is less than x. Okay, that y is less than x. What do we think? Do we think this is true or false? Right? So just like as an example, right? Like if I choose x equals 5, then is there a y value, which is also a natural number, such that y is less than it? Yeah, like y equals 2, right? It's not saying there is a unique one. It's just saying that there is one, right? So what is important here is that it's true for all x values in the set, for all x values. I got 2 falses in the chat here. Anybody want to elaborate why it's false? If you don't want to, you don't have to. It's fine. I'll elaborate no matter what. But yeah, so I got an x equals 1, right? So that's very important. It has to work for all of them. But if you choose x equal to 1, which is an element of the set, now try to find a number that is smaller than it, right? Well, you can't say 0.9 because 0.9 is not an element of the set. Okay? You can't say 0 because 0 is not an element of the set. There is no such y value. There is no y such that y is less than x. Okay, so let's formally prove this. So to prove a statement to be false, you prove its negation, right? You prove its negation. So so right now, this is false, right? And we want to prove it. So we're going to prove the negation of, for all x that are elements of the natural numbers. Let me write this better. Okay. Screwing up my n here a little bit. There you go. It's a little better. There exists. I can do better than that. I can do better than that. Come on. Already bad. And that's as good as we're going to get. That's pretty bad. For all n x that are natural numbers, there exists a y that's an element of the natural numbers. There you go. That time was better. Such that y is greater than less than x. Yeah. So a counterexample would be a I guess. A counterexample where it's not true, like showing that there's an element of x. Yeah, I guess so. How would you phrase that in a way that's... Yeah, okay. I'm going to still do it like this because I still want to show taking the negation of a big statement like this. But yeah, I think that would probably be fine. I'm not marking this, but yeah. So we're trying to prove this, okay? So the negation, you just kind of distribute this negation into there, right? Counterexample would be an element of the negation domain. Yeah, it would be an element. It would be an element where the statement is false for, right? The statement that we're claiming is true for all. Anyways, my point right now is to how to take the negation of this kind of thing. So the negation of for all is, there exists. Let's just think of this logically. We're saying that for all x in n, there is a y such that the statement. Well, the opposite of that is there exists some x in n such that for all y, that statement's false. There's no way to find a number that works for. So for all x in n, there exists an x in n, such that for all y in n, the opposite of this, which is that y is greater than equal to x. And then you can prove this statement by just instantiating it, right? By finding such an element, and x equals 1. Right? Because this element, which is an element of n, for all y in n, y is either equal to or greater than this x value. And that would be, we would be done. Just put a little square. To prove this true, we're right now in this second statement here, we're proving the existence of something. To prove the existence of something, you just have to instantiate it. You just have to come up with it, right? Show me, right? That it exists, or at least show me a way to get it. In this case, we can do better than that. We can just show the number, right? We can just say, okay, x equals 1. Right? That is an element of n for which this statement is true, the negation of what we're trying to show. So we must have proven that the original statement is false. And the such that doesn't change this. It's such that the negation. You see, like, well, the such that did change, right? Like, x less than y, y greater than or equal to x. Right. So the negate, like the such that is just a word, right? So like it's the statement after it that we're interested in. Yeah, I mean, yeah. Can you just at this, like, you have the idea at this point. At this point, like, everybody's saying x equals 1. Not everybody, but people are saying x equals 1, right? Is an example for which this fails. Yeah, I mean, that's fine. Like, that should be fine. This is not the only way to prove it. I mean, but this is definitely how it's expected of you to prove it. Getting the idea of, like, instantiating this x equals 1. Really, the difficult part of this is understanding the symbols, and then it's clear, well, x equals 1, right? 1 is, you know, a smallest element here. There is no element that is smaller than it. Probably just finding a counterexample right at the start would be full marks. Is there a certain format for proofs, or could you just say x equals 1 is a counterexample and give a written reasoning? Yeah, I mean, there definitely is a format for proofs, but that's not to say it's set in stone at all, right? Like, there's just nice things to like, proofs are all about communicating rigorous ideas, right? You're just trying to communicate. So there's no, like, algorithm for a proof, right? There's no algorithm to decide how to talk, right? Okay, we have LLMs and stuff like this anyways. But, you know, aside from that, disregarding LLMs, we have there's no algorithm for that. So there's no algorithm to, like, write a proof. But there are nice standards that we have. And I'd encourage you to read the textbook, which has a big list of all the standards of how we do it. Should we always just negate the statement for proofs? I mean, yeah, if I'm trying to prove something to be false, logically this means I have to prove the negation. And I think they expect that of you. I'm not writing or marking this test. But I think they expect you to understand that if you're trying to prove something false, you have to prove the negation of your original statement. Couldn't you let y equals x minus 1, then it would be true, or would that be illegal, since if x equals 1, then y equals 0, and that would not be natural? Correct. You can't just say, yeah, like, it's fine to say y equals x minus 1, but that fails when x is 0, right? Or when x is 1, because then y is 0. 0 is not an element. 0 is not. See, and you see, y is an element of the natural numbers. 0 is not an element. Do we always have to prove the negation, or is counterexample sufficient? I mean, it's really the same thing. Like, you're really doing the same thing, right? By providing a counterexample, you're providing an example of the negation, right? So it's really the same thing. So now that you have all the negation written, all you have to show is that there is one particular non-generic x, like x equals 1, just that for y, for any y, no matter what it is, the negation is true. I.e., you cannot say y is not arbitrary. It is not arbitrary. Yeah, like, I agree with you. That's what we did. You cannot say y equals not. Like, the fact that I pulled up like a real, like, actual number for this last step is because I'm trying to prove the existence of something. And one way to prove the existence of something is just to show that thing. I'm proving that a cow, cows exist. If I just pointed to a cow, then that proves that cows exist. So that is a product not of the method that we're doing here. That is a product of what I'm trying to prove at the end here, which is the existence of something. Okay. Keep the questions coming. If you got more questions, please. I'm happy to explain. But yeah, so this is a really fun part. You really get to talk about numbers here, because the next question, right, is counterexamples always used? No, but that is most likely what is expected of you in this course, right? To, like, figure out if you're trying to prove the existence of something, then you should come up with an example of that thing. In reality, you can just provide an algorithm to find that thing. That's really good enough, but that's a little complicated, so we don't have to do that. Okay, so take a moment here so people can process this as well. Someone asked, slightly unrelated, but since you're in 4th year, what upper year courses does this course tie into? I mean, proofs, like some algorithm classes, right? So you can take CPS 688 if you're a computer engineer. CPS 688 has some proofs in it, but really there's no proof writing. It's just to understand what proofs are, how to read proofs, and that's an important thing. I think that is important to be a computer scientist or to work in algorithm design and stuff like that. But otherwise, like in terms of actual courses, I mean, I don't prove anything. I don't know. Like, there are no proofs. The closest I've gotten to proofs are in my math courses. Like I did a math minor, so like in my math minor courses, but not in eng courses. Engineers don't prove things. This is the only time engineers prove things. Engineers read proofs, but that's it. I mean, I'm way overgeneralizing here, right? Like, of course, you can be an engineer and write proofs, but it's not a common requirement for engineers. So an algorithm is not required as long as counterexample is provided, correct? Are you a computer engineer? Yes, I'm a computer hardware engineer. Follow-up, does it ever get better? It does. It does when you're done. When you're done, it gets better. I can't say that fourth year is easy, right? Fourth year is hard, a lot of time. But yeah, like when you're done, you're done. I mean, I'm going to master's next year, so I'm not done. But anyways, master's is apparently, so I've heard, a lot easier. Or not easier, but a lot more control of your time, I guess, which is the main thing that we lack as engineers. Okay, I will continue. So this next statement that we're trying to prove, it says for all x in the open interval meaning not including the bounds, open interval 0 to 1, there exists some y in the open interval such that y is less than x. Okay, so let's draw this out a little bit. So the open interval from 0 to 1 kind of looks like this. I'm going to draw it like this, just to remind you, not including the endpoints. Okay? It's the open interval from 0 to 1. And we're saying that for any element in this, now keep in mind here, this is a subset of the real line, right? The real line is what we call dense. So there's, between 0.6 and 0.7, there's another infinite amount of numbers between there, right? That's what we call dense. And so that's an important point here, that we're gonna come up with that. We're going to use that fact, essentially. Anyways, so for all x, the element of 0 to 1, there exists a y from 0 to 1 such that y is smaller. As in, doesn't matter what number we take in this set, I can always find a number that is smaller. That's what this is saying. I can take, for all x that are in 0 to 1, so I can take any element in 0 to 1. Then, corresponding with that element, there exists another element, not equal to x, but we didn't say that yet. But anyways, there exists another element, y, in 0 to 1, such that y is smaller than x. Now, to be clear, that y doesn't have to be smaller than every x value. Y has to be smaller than the x value that we chose from 0 to 1. So let's say, okay, first of all, do you think it's true or false? What do you think? I'm getting a couple trues. Getting a couple trues. I got a capital T true as well. Extra. 0 and 1 are not included. Got an all caps true as well. Got an IDK. Fair enough. Can you divide 2 for every chosen x? Yes, exactly. Is it not false if you choose 0? You can't choose 0. 0 is not in the bounds, right? Right? 0 is not in the bounds. 0 is not included. It's an open interval. So I would agree that this is a true statement because regardless, so I just prove this fact. Essentially, the way you can prove this fact is to show an algorithm. Essentially, to start with, let's say you choose x is an element of 0 to 1. Let's just call it x naught. Right? Then we can choose y, which is x naught over 2 or over 3 or over 4, whatever. Anyways, which is certainly smaller. How should I write this? Y is x over 2. So y is certainly smaller than x naught. Say y naught is certainly smaller than certainly smaller than x naught. Y and y is an element of 0 to 1. Therefore true. That's not really a super nice way to conclude this, but therefore true. Right? And there we go. So we figured out how. So essentially, what I'm doing is I've shown an algorithm this time. I've shown an algorithm of how to select this step right here. This step is the algorithm, right? To show how to choose the y value from 0 to 1 that is less than x, the x that you chose, x naught, the x naught that you chose. And this works for all x naught. You can divide, this is not something like, to prove this here, but like you can divide all the numbers from 0 to 1 by 2, and that value will always be closer to 0, will always be smaller. Right? Oops. So since you can divide it by 2 and you get a smaller number, this will always work. Right? What this is basically saying, right, is that there is no smallest number in 0 to 1. There is no least element, essentially, right? Right? Like there's no element of 0 to 1 which is smaller than everything else, right? Like you can choose 0.00001, but you can always get a smaller number by just dividing it by 2. That'll always be smaller. So there we go. You can divide it by 10. You can divide it whatever. 2 is arbitrary here. Let's just make that clear, right? 2 is arbitrary. 2 is arbitrary. And then, true. Like, made it clear, it said true. And, just do your little proof sign, and there you go. Just 3 lines. Could have been 1 line, but, so, like, if you wanted to add more words, something to this, right, you could say, like, pick, set, then, and now it's a full proof. Proofs don't have a structure like this. It's about communicating your ideas. That's what proofs are about, right? We have standards of how we communicate it, and logically, it has to be cohesive, like logically, but not in terms of writing. How do you prove something if you don't know if it's true or false? How would you go about doing that? Okay, so let's say I have no idea if this is true or false, right? Then maybe I'd assume that it's false, and I'd try to find a counterexample. And in my attempt to find a counterexample, as in some way to prove it false by making a counterexample, maybe then I'll learn why it's actually true, because maybe I won't be able to find a counterexample. And then by playing around with it a little bit, you might realize, okay, so it's actually true, and then you can work that into the proof, what you just experimented with. But I'd probably start with assuming it's false, trying to prove it's false, and trying to find a counterexample. What do you mean by 2 is arbitrary? I mean by 2 is arbitrary because I could have put I could have put 5 here. That would also work, right? Like x naught divided by 5. That's also smaller than x, and also in 0 to 1. Right? That's what I mean by arbitrary. Now it's not random. Like I couldn't choose 0.1 here. That's not good. That would make it bigger. But it's not uniformly distributed random. But you can just choose whatever number you want here. Essentially, like just choose 2. It's the simplest number you can choose. Can't choose 1 because 1 is not doing anything. You just want to make it smaller. You could also, like, whatever, if you wanted to choose, like, 4 over 5 x naught, whatever, sure. That's smaller, right? That's going to be smaller than x naught. It's just something that makes it smaller. That is still an element from 0 to 1. So you couldn't subtract 1. That's very important. You could not subtract 1. Because if you subtracted 1, that would go out of the bounds, right? If I chose x naught equal to, 0.7, and then I chose my y naught to be x naught minus 1, then y naught would be negative 0.3. No good. That's out of the bounds. But if I choose my y naught to be x naught over 2, okay, now we're good. Now we're at 0.35. That's still in the bounds. It's still 0 to 1. All good. Okay. That is that question. Anybody has any more questions, please let me know. Otherwise, I will continue to the next page. Well, I guess I should have the chat open. If I say, please ask any more questions, I should probably have the chat open. no questions in the chat, so I am good. If I could minimize it, that'd be good. There we go. So the next thing is continuing with... sorry. Clicked the wrong thing. So the next thing is continuing with proofs. We want to prove another statement. This statement is the fact that this number is even for any integer a, that this will always be even. In other words, like, you know, it's written in English here, but let's convert it to symbolic form, right? You know, for all a that is an element of the integers, 2a minus 3 minus 7a. Or sorry, there exists some k that's an integer such that 2a minus 3 minus 7a equals 2k. So for all a in z, there exists some k in z that makes this true. That this is equal to some even number. Double some integer, right? Double an integer is exactly the definition of an even number. Now, you don't need to say that. I'm just a little exercise. You don't need to convert it to symbolic form. I'm just something to think about here. Maybe the next one I'll ask the chat to do. But yeah, so let's continue. Let's prove this. So the way I would probably do it, like, you know, you can start by trying to find a counterexample, but why? Well, like, you have some stuff you can do here, right? You could first of all distribute this. 4a minus 6 minus 7a. And if you could factor out a 2 from everything, it would be even, right? Like, because it would be 2 times an integer. But we will just attempt that. We'll see, right? So 2 is 4a minus 6 minus 7a. So I can combine this negative 3a minus 6. And I can factor out a negative 3 if I want as a plus 2. Okay, so we're here now. Now we want to somehow prove, like, we want to somehow determine, like, I don't know right now. I know, but let's say we don't know if this is true or false, right? You might just want to, like, plug in some numbers, see what happens. This is a much more simplified form, though, right? So it's good to write it like this. I don't know, so just, like, try a equals... but you can't factor out a 2, right? Because it's gonna 3 doesn't divide by 2. Like, let's say you did. So sorry, question in the chat. Why don't you factor out? Okay, yeah, someone. Let's still say it. Why don't you factor out a 2? Because if you did, sure, it'd be great. That would almost prove that it's even, except that it'd be negative 3 over 2a minus 2, right? No good, because this is an integer. An even number is an integer, right? So yeah, like, but this is not an integer anymore, right? It's a rational number, so no good. We've introduced rational numbers. Unless somehow we could prove that turns into a rational an integer, then we could do that, but we can't. A plus 2. Yeah, exactly. So, like, just try a number, right? So if you just, like, choose a equals 0, then it's like negative 3 times 2, which is negative 6. Ah, look, it's even. But then if you, like, try a equals 1, then you get negative 3 times 3, which is negative 9. Ah, it's odd. Okay, so it's false. So that what that means is that we can again, like, there's a few ways you can communicate this. You can prove the negation. You can say, like, take the negation of this, that there exists an a and z such that for all k, it is not a, or for all, there exists an a and z such that that is an odd number. You know, so essentially we can say here, right? So, you know, this is odd. This is, you know, a in z. And, like, if I was marking this test, I would say that this is fine. This is good enough. You've obviously gotten the point where you can generate a counterexample here, right? So it's not always going to be even. It's not always going to be odd. It depends on a, right? Like, it fully depends on a. So you just want to generate an example. Can we do a proof and then do a counterexample, sweeten the deal to get 100? I would do that. Yeah, so it's false. Someone asked, so it's false? Yes, it is false. We've showed it. So it could be both even and odd. Well, yeah, like this expression is both even and odd. Well, no, like the parity, like the even and oddness of this expression depends on A. It's not always even. It's not always odd, right? It just depends on A. So it's not that it's both. It's just that we don't know until we plug in A. But the statement is that, yeah, it's exactly. So it's up to you to prove your chosen argument. Yes. But the statement is that that expression is even for any integer. Well, I found an integer that I can plug into it and I get an odd number. So it's false. Therefore, false. Do we need to negate the symbolic form for the proof? Can you show this, for instance? For example, if the question asks to use symbolic proof in your proof statement. Yeah. So if I were writing this, I would prove the negation, right? So maybe I would let's just write that quickly. So proof So I take the negation of this. So that is even for any integer a. Well, there exists some integer a such that this is odd, right? Let's look at, we're trying to prove not whatever. It's simplified to negative 3a plus 2, right? So let's just use that. Negative 3a plus 2 is even for all a in Z. Okay, let's write it out a little bit more symbolically. For all a in Z, let's just say negative 3a plus 2 is even. That's fine. You can say that. You don't have to write it out with the k and all that. So now I'm going to take the negation. So that means there exists some a in Z such that negative 3a plus 2 is odd. And I will prove the statement by instantiation, by just giving you an example. A equals 1. There. And now it's proved. A equals 1. Negative 3, 1, a plus 2 equals negative 3 times 1 plus 2, which equals negative 9. I don't mark. So someone's asking me, do I need to write the second part? I only need to write the first part. I mean, I don't mark the tests. I don't know. But if your teacher in lecture has communicated to you that they expect really formal proofs like this, then this is how you would do it. You definitely won't get 0 for doing it this way. You just might not get 100% for doing it this first way. Maybe you'll get 100%. I don't know. Again, there is no direct structure here. Can you go over how you got the symbolic form at the very end, at the very start of the question? How exactly did you get the original symbolic form? Yeah, I a little overdid it here. But for all a and z statement, right? Okay, so what's the statement? The statement is that this is even. What does it mean for that to be even? Well, for that to be even, that means there exists some k and z such that it is equal to double that k. All of this is just kind of saying, all that and that is just saying is even. But I think it's a little cleaner to this is totally just as rigorous and fine. This is nicer. So I prefer this way. Okay, so that is that question. If there's any questions, please let me know. Otherwise, we got, I think, just one more. Oh, no. A couple. Okay, so this next one is if, let me just open the chat again. So this next one here, if n is 4k for some integer k, then if n is 4k for some integer k, then n is even. So what do you guys think? Easy peasy, I got. True. Yes, it is true, right? So this one's easy. Because we just have to figure out what even means. Even means it's double some integer. So if n equals 4k, well, that means that it's 2 times 2k, right? 2k is an integer. K is an element, k is integer. Therefore, 2k is integer. Let's say 2k equals k naught is integer. So you can write this as 2 times k naught. Logically implies n is even. And there we go. That's really it. So we just show from n equals 4k, which is 2 times 2k. Well, 2k is an integer. K is an integer, so 2k is an integer. So 2 times k naught, which I'll call 2k. N is that, so it's even. Pretty straightforward question, but if anybody has problems, please feel free to ask me. Can you write in symbolic form for me, because Prof is really focused on getting words into symbolic form? Yeah, I remember that too, like from last year when I taught this. So the Prof likes symbolic form. But symbolic form for this is not very complicated. Like it's just like n equals 4k implies n is even. Well, implies there exists some k. Like if you really wanted formally, k and z such that n equals 2k. Like that's the really symbolic form. If you want a little bit more relaxed, again, proofs are really just about communicating. You got to communicate correctly. Like the things you're saying have to be right, but it's really just about communicating. So you can just say it implies n is even. What if it's the opposite? If n is even, then n equals 4k for some integer k. Yeah. What do you think if it's the inverse here? Or the converse, I forget which one it is, right? Yeah, let's just as an example here, right? If n equals 4k, sorry, if n is even, then n equals 4k. What do we think about this? Is this true or false? I got one false. And that's all I got. So it looks like that's what everybody thinks. This guy will speak for all of you. And I would agree. So there we go. Got another false. So yeah, so basically we're showing that n is even implies n equals 4k. Well, I can, prove the negation of this, right? It's false, right? I can prove the negation of this. The negation of n is even, so this means not. So remember, p implies q is the same thing as not p or q. So not n is even or n is equal to 4k. Okay, well, distribute the not in, right? So not n is even and n is equal to 4k. What am I doing? Hold on. I'm proving the negation of this. Not n is equal to 4k. Prove this. Yeah, I missed some words here. For what am I saying? For all. Yeah. I missed some words. Yeah, wait. No, I think that's right. But, oh, yes, there you go. I agree. I agree. Not equal. There's a not equal missing there. So I'm trying to find. This basically means like, okay, I have to show. Okay, for all n in Z, if n is even. So I'm taking the negation of this, right? So then what I'm saying is, the negation of for all n element of Z. This. So what I'm saying is that there exists some n in Z. Sorry, I should have written that first. I'm just saying there exists some n in Z such that n is even and n is not 4k. I mean, there's a lot of work to just kind of say the same thing we're saying, like that there is some number that is even and not a multiple of 4. But to prove this is very easy. Like it just instantiate it. Like if you're proving the existence of something, you just have to just give it. So like n is even, n is not 4k, like n equals 6, for example, right? N equals 2, whatever. N equals 6 is even, but it is not equal to a multiple of 4. So you're done. So this is false, this statement. Okay, that's that. So next part. Okay. I mean, for full marks, you would say 4 cannot divide 6 without... Like, you don't really need to say that. You don't need to bring in the rational number stuff. I don't think. It's also like, it depends on who's marking it, right? But depends on what your teacher communicated to you is expected. How did you get n is not equal to 4k? What law is this? I'm just taking the negation. So this negation here, this negation hops in here. Well, okay, so first of all, hops in here, switches the for all to there exists. Hops in here, negates this negation, so it's just n is even. Hops to the or, switches it to an and hops into the q, which is n equals 4k, to n is not 4k. Does that clarify it? Okay, so let's move on. Boom, boom, boom. So, the next question is prove that if x cubed is even, then x is even. Whenever you do this, it's easier to not start with the thing that's being cubed, right? So right now, like what we're trying to prove is that x cubed is even implies x is even. So you could start this by saying like x cubed equals 2k for some integer k. But this gets complicated because then you're going to take the cube root and blah, 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 blah. Okay? It's good not to start with the cube. So what you can do is you can do the contrapositive. The contrapositive is you swap the order and you invert it. Right? So it's not x is even implies not x cubed is even. So this is called the contrapositive, right? You just swap it. A logical implication is equivalent to its contrapositive. So this is the contrapositive. This is the easiest way of doing it. Let's see what the questions. I got a question in the chat. Can you use the quotient rule? What do you mean by quotient rule? Like the quotient remainder theorem? What do you mean by quotient rule? But how would you show, but you still have to deal with a cube. I don't know how you deal with the cube. Can you prove by contradiction? Probably. Do you want me to do that? I can do that, sure. But proving it by contradiction is like you're going through some loops that you don't really need to go through. But yeah, Probably. Anyways, proving the contrapositive is easy, right? Because the negation of x is even is x is odd. Well, it's not easy, but I'm exaggerating here a little bit. But x is odd implies x cubed is odd. This is relatively simple to prove because you just start with, okay, well, x is odd. That means x is equal to 2k plus 1, for some k in z. Right? Then x cubed is going to be 2k plus 1 cubed. Okay, well, we can just kind of expand this out. So it's going to be, 2k squared is going to be 4k squared plus 2k plus 1 times 2k plus 1, and you just expand this out a little bit, so you get, I did it earlier, so I'll just do it. This question I did earlier. What did I say? So I just got that this is 8 k cubed plus, or actually, yeah, you actually don't even have to do this, but anyways, this works. So 8k squared plus 4k plus 1. And from here, right, you can factor a 2 out of the first 3 terms. So you get 4k cubed plus 4k squared plus 2k plus 1. But notice where the bracket closed there. And, since k is an integer, right, k is an integer, all this is an integer, is an element of z, right? Call this k naught. So then we have that this is, equal to 2k naught plus 1. Therefore, x cubed is odd. That's the definition of odd, right? 1 above a multiple of 2. It's the definition of odd. So we started with x is odd, and we concluded that x cubed is odd. You could have actually just alternate here, just to give you a little idea here, right? Alternative. You could have said that x cubed equals same start 2k plus 1 cubed, which is 4k squared plus 2k plus 1, 2k plus 1. And you can, sorry, I know my k's are bad. Anyways. So, this is clearly an odd number, right? Because it's 1 above a multiple of 2. This is also an odd number, right? So you could write this as 2k squared plus k plus 1 times 2k plus 1, right? And so we have odd times odd, which is odd, times odd, which always results in an odd number. But you'd have to separately prove that, I guess, right? That an odd number times an odd number is always an odd number. But anyways, here, assuming that's true, then that's a conclusion you can make. Should we state that k equals 4k cubed and prove that? Oh, you don't have to prove. No. You don't have to prove. Yeah. I know what you're saying. It's like, I just said to you that this value in here is an integer. I don't think you have to prove that. That's like, how are you going to prove that? Like, you're going to say 2 times an integer is an integer. The square of an integer is an integer. 4 times an integer is an integer. Adding up integers is integers. That's all you're going to say, right? Like, you're just going to say that over and over again. So there's nothing really to prove. If you really wanted to get into it, like, why is 2 times an integer, then you're gonna have some writing to do, right? Why? But I highly doubt that's expected of you in this class. You could let x equal 2k and then just cube that and factor out a 2 to prove it's even. But isn't that going the other way? That's going the wrong way. That's saying x is even implies x cubed is even. But that's not what this is actually asking. What you proved by saying that is prove that prove that if x is even, then x cubed is even. But that's not the same, is what we say here, right? Yeah. No problem. How do we know that we should use the contrapositive? How do we know which method to use? So my logic with this one is yeah, I said use the contrapositive, but let's just start from scratch. Looking at this question, well, first thing is like get the implication. So there's our implication, right? There's our implication. Okay, well, probably the next thing you do is you'd say, okay, well, x cubed is equal to 2k. But again, you're a little stuck now. Like I don't know what to do. In general, it's bad to start with like the exponent. So whenever you are a little stuck and you're doing an implication, always think in the back of your mind, you could take the contrapositive. You could flip the order and negate them. And they're logically equivalent. So you can always do that. Anyways, that's that question. Okie dokie. So let's open the next page. So next page says, show that the following argument is invalid using a truth table. Back to the good old truth tables. So this is really good. This is a good example. It's also a fallacy that people fall in all the time, right? Which is like P implies Q, Q, therefore P. Right? So, an example of this is like, it's raining. It's raining implies, the ground is wet. The ground is wet, therefore it's raining. But the thing is that there's lots of other reasons that the ground could be wet. And we're completely ignoring all those other reasons. We're claiming that there is the only one reason that the ground could be wet. And we're claiming that there's a double arrow here. The double arrow is saying that P if and only if Q. It's raining implies that the ground is wet, and the ground is wet implies that it's raining. That these two things happen only together and with nothing else individually. But that's not true. So this is a common logical fallacy. Anyway, so we make a truth table. So to start the truth table off here, you start with P and Q, right? Because those are your logical values here. Small truth table, true. Well, I'll start with false, false. False, 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 true, true, false, true, true. Then I would get P implies Q. P implies Q, remember, is an implication. Implications are what we call vacuously true or just automatically true if the P is false. So true, true. Okay, now this next one is false because the P is true, but the Q is false. So it's not true that P implies Q. And then true for this last one. And then this last row is just Q. Just for formality, we just rewrite it. Okay. And then put a little line here just to kind of differentiate what's going on. The last step is we put our conclusion, which again, we just rewrite for formality's sake. And now we want to highlight rows. They're called critical rows. Critical rows are where both of the arguments, both of the, I forgot the word, but whatever, arguments or lines that you're making in your argument. No, both of the predicates, premises. Yeah, both of the premises. There you go. I think that's the right word. Both the premises are true. So that's right here. And that's right here. And necessarily, if this argument is valid, that means that if both of those premises are true, then the conclusion must be true. That's true down here, but that is not true here. This is the problem. Right? This is the problem right here. Oops. Come on. So right here, both premises are true. But the conclusion is false. therefore invalid. And we are done. Still have time, so we can do some more stuff for half an hour here, but we're done the midterm. I do not have access to the homework questions. Is there going to be things from midterm 2?
Our prof said there was going to be some of it because we're only having one midterm this semester. So a few questions off midterm 2 will be on this.
And is that some stuff that we haven't talked about yet?
Yep.
What is that stuff? Like what is
The first few questions on midterm 2.
I don't know if I have midterm 2. Oh, that's what they mean. That's what you mean midterm 2. Oh, okay, I don't think I have midterm 2. I have midterm 1A and 1B. If someone would like to email it to me, we can take a look. Well, I just did 1B. Okay, here. If someone wants to email it to me, please do. I will put my email on screen. And we can give it a shot. Or if you want me to put it in the chat, I can put it in the chat. Hopefully I don't get 20 emails. Okay, I got the emails. Thank you, guys. Well, I got it on my iPad, but not on my computer. There we go. I got it. Thank you, guys. So, sorry, computer's super slow. Okay, 2A and 2B. So let's take a look at this together. There's a couple of them, right? So it says prove that the sum of 3 consecutive integers is divisible by 3. Use the quotient remainder theorem to prove that the product of any 2 consecutive integers has the form that or that. Prove the following by contradiction. So like this kind of stuff, right? This is the... Oh, but I'm assuming not induction. There's no induction, because that would be a whole thing to talk about.
I believe you're correct.
Okay, sounds good. Okay, let's try these. So it says, prove that the sum of 3 consecutive integers is divisible by 3. This is not hard. So let me just be clear. This is midterm 2.
I think so.
Yeah, sorry.
Oh no, I was just confirming that it's midterm 2.
Yeah, okay. Yeah. So prove that the sum of 3 consecutive integers is divisible by 3. So the sum of 3 consecutive integers looks like x plus 1 plus x plus 2. Right? This is the sum of 3 consecutive integers. Yeah, x is an element of z. Okay, well, that's going to be 3x plus 3. Oops. Right? Okay, so, now we're asking, is this, is this divisible by 3? Right? So let's say n, 3 divides n, right? N is divisible by 3, as in 3 divides n. It implies that n equals 3k for some k in z. Okay, that's what it means for something to be divisible by 3, is that it is a multiple of 3. I think everybody understands what a multiple of 3 is, so that's what it means for something to be divisible by 3. So we just have to prove that it's a multiple of 3. Well, I mean, that's not hard because you can just factor out a 3 and you get x plus 1, right? Call this, I guess I shouldn't use x here really, right? But anyways, too late. So they call this x naught, which is an element, which is an integer, right? X plus 1 is an integer. Therefore, this is equal to 3 times x naught. Okay. Therefore, 3 divides, let's that. Give a symbol, I don't know. P, right? 3 divides P. Or I guess S for some. S. Make that an S. There you go. We're done. A little bit of a mess though. Let me speak over that again. S is equal to the sum. There's our sum. Well, that sum is also equal to this, right? It's going to just combine like terms. And that sum is also equal to this, which means that it implies to us, implies to us is 3 times some x naught, which means that 3 divides s, which means that s is divisible by 3. And so let me just highlight like this. What I mean by this is I'm just indicating to you what that means for n to be divisible by 3. And n is not part of the question. I'm just giving you the fact of what it means to say 3 divides n.
Could I also just find like an example of this?
Yeah, it's got a little bit poorly phrased, but it's supposed to be like prove that the sum of any 3 consecutive integers.
Okay, I see.
Like that's what I'm assuming is meant here. Yeah. You could, if it was proved that there exists 3 consecutive integers such that their sum is divisible by 3, then yeah, just give an example. But I'm assuming it's like prove that the sum of any 3 consecutive integers is divisible by 3. Okay, so there's that. Got emailed the question. Sounds good. We can take a look at that, but let's finish these first. So the next one says using quotient remainder theorem, it's d equal to 3. Prove that the product of any 2 consecutive integers has the form that or that. Okay. So the product of any 2 consecutive integers, that means, let's pick some n is an element of, and it is an integer, right? Then our product that we're forming is going to be n plus 1, n plus 2, right? Prove that the product of any 2 consecutive integers has the form like that. Well, n is an integer. Since n is an integer, we can break this into cases, right? So this is a little bit getting into like modular stuff, but basically, if n is an integer, then let's just say 3. Let's pick, picking 3 here. Not that n is 3, but let's use 3 as a base point. N is either a multiple of 3, it's either 1 above a multiple of 3, it could be 2 above a multiple of 3, and that's the only options, right? Because it can't be 3 above a multiple of 3. That's still a multiple of 3. So we have 3 cases, right? So quotient remainder theorem says that we have a few cases here. Case 1, n is equal to 3k plus 0. Case 2, n is equal to 3k plus 1. And case 3, n is equal to 3k plus 2. And there's no other options. N is either a multiple of 3, 1 above a multiple of 3, or 2 above a multiple of 3. And these are non-overlapping, right, and unique. So you just prove it for each case individually. So for case 1, color shirts there. For case 1, n equals 3k, then our product equals 3k plus 1. What are we trying to show? We're trying to show 3k, yeah. I guess I shouldn't choose k because k's here. So I'll just choose r. Well, it can't be r. It's a good letter. Can't be n. Okay, I'll choose k naught. K naught. Okay, so 3k naught, k naught, k naught. So we want to show that this product is equal to 3 times some integer, or it's 2 above 3 times some integer. Well, in this case, that's pretty easy, because you can say that this is 3 times k naught times 3k naught plus 1. That is an integer. We're done. Therefore, this equals to 3k. We're not done the whole question. We're done case 1. I show that it's one of these two forms. 3k. For case 2, n is equal to 3k naught plus 1. Okay. So p, I have a message in the chat. Let's see the message in the chat. Nothing. Good. Yeah. Okay. So we have it's k, right? It's k times n plus 1. So it's going to be 3k plus 1, 3k naught plus 1, and then 3k naught plus 2. Yeah, what allows you to assume that n is one of the 3 cases and absolutely nothing else? This is quotient remainder theorem. So if you look at the statement of quotient remainder theorem, is that it breaks it up. Nothing special about 3 here, though, right? So if I chose instead 5, then I had 5 cases. N would be a multiple of 5. N would be 1 above a multiple of 5. N would be 2 above a multiple of 5. N would be 3 above a multiple of 5. And N would be 4 above a multiple of 5. And that's it. You can't go further because then, right, N equals 5k plus 5. No good. That's still a multiple of 5, right? That's back to case 1. There's no other case. So this is, QRT with D equal to 5. This is, hint D equals 3. So tell us use D equals 3. And they'll give you the hint. Knowing to do that is a little tricky, but I mean, yeah, like the 3 kind of gives that away here, right? That you need, because you need to have 3 times an integer. But not necessarily always the case. Very important proof method that we have and this only works for natural numbers, right? Or for integers. Anyways, FOIL all this out, you're going to get what? You're going to get 9k squared plus 6k plus 3k, or k naught, right? 3k naught plus 3. And again, you can just factor a 3 out of this. So you get 3k naught squared plus 6k naught, or 6, or sorry, 2k naught plus k naught plus 1. And again, that's an integer, right? I don't know what integer, but that's an integer. Therefore, this is equal to 3k. Where would it be 2? How'd you get 3? Where? Oh, yeah. Yep. Absolutely. So that's a 2 there. So you cannot factor out a 3. You can only factor out a 3 from the first few terms. Still, this is all k. And we showed that it's now in the second form. It's 3k plus 2. Thank you. It's always 2 times 1 that gets you. Case 3. N equals 3k plus 2. And from here, we can just say that P is equal to, well, again, it's n plus 1, right? So it's 3k naught plus 2, 3k naught plus 3, and we follow this out. 9k naught squared plus 9, what am I saying? Yeah, plus 9k naught plus 6k naught plus 6, and from this you can factor out a 3, so you get 3k naught squared plus 3k naught plus 2k naught plus 2. And again, all of this is equal to your k. Therefore, we have that this is just 3k. And so you see that no matter what, in any of the cases, it's always either 3 times the multiple of k, or it's either a multiple of k, or it's 2 above the multiple of k. No matter what. The product of any 2 consecutive integers will either be a multiple of k, multiple of 3, or 2 above a multiple of 3. 2 above a multiple of 3 is the same thing as 1 below a multiple of 3. So,
Can you scroll back to the bottom one for one sec?
to the which one? Sorry. This one?
The last one you did there?
Oh, this one? Thank you.
Yeah. I'm good.
Sounds good. So, yeah. There we go. That is that's that question done. Someone said that there would be contradiction. So there's one more example on this test that's with contradiction. We can try it. Let's see what it says. It says, prove the following by contradiction. Let x and y be integers. If x and y satisfy this equation, then at least one is odd. Someone asked the question, how come for case 2 we don't get 3k instead we get 3k plus 2? Well, I mean, basically what we're saying is that if your starting integer is 1 above a multiple of 3, then the result you get is 2 above multiple of 3, right? So if you take like 4, which is 1 above multiple of 3, multiplied by 5, right, we get 20. 20 is 2 above a multiple of 3. 6 times 3 is 18. So it's 2 above. Okay? So that's all we're saying. We're just saying in that special case where the first number you choose is 1 above a multiple of 3. That's that. I mean, why? Right here. Why? That's why. If you want a deep number theory reason, I don't really have a deep number theory reason for you here. But proof of it is right there. So let's try to answer this one. So prove the following by contradiction. So it says, let x and y be integers. If x and y satisfy this equation, then at least one of x and y is odd. So, okay, so it says by contradiction. So you got to suppose the opposite of what you're saying, right? So suppose, by contradiction, that x and y are both even. Let's just that not x, okay, yeah, x and y are both even. X and y are both even. So let x and y be integers. If x and y satisfy this equation, then at least one of x and y is odd. Suppose for contradiction that x and y are both even. Then what we're going to show is that there's no way that they can solve that equation there. So is the conclusion true based on case 2? Yeah, because so back to this question, someone was just asking, is the conclusion true based on case 2? It's giving it to it, so like it's in the form 3k or it's in the form 3k plus 2. One of those two forms in the question. It's not just saying it has to be 3k. 3k or 3k plus 2. So yeah, it's fine, right? Because we showed. Okay. So suppose by contradiction that x and y are both even. If they're both even, then we try to sub it in. We get 3 times 2k1. Okay, let's, x equals 2k1, y equals 2k2. So that means 3k1, 3 times 2k1 plus 5 times 2k2 equals 153. In other words, well, okay, so what's the contradiction here? Like, what's the contradiction? Yeah, what do you think? What's wrong with this? There's something wrong with this equation. This equation has no solutions for k1 and k2. There are no solutions. As in, x and y don't satisfy. Yeah. So the left-hand side is even, and the right-hand side is odd. An even number cannot be equal to an odd number. So you can factor out 2. It's 3k1 plus 5k2 is equal to 153. Right? This is even. Even. This is odd. This is logically impossible. We know that integers are either even or odd. There's no way for an integer to be both even and odd. Now, that's something you can additionally prove here. If you want to prove that there's no way that an integer can be both even and odd, we can prove that. But no, they're like at the moment you can just take that as a statement that even, an even integer cannot be equal to an odd integer. Contradiction. Therefore, one of either x or y is odd. Or not, it doesn't mean one of, I guess. At least one of. One of, or both. Or both here. So someone's asking, where is the contradiction part? Someone unmuted there, but let me answer the chat question first. Where is the contradiction part in the question? Is it when we took both to be even? So the contradiction is where, first of all, we're supposing that x and y are both even. That's not the contradiction. That's just our supposition. That's like what we're saying, And we're going to show that by assuming that, it leads to something that cannot be true, a contradiction. Right? But this is fine. This is just our assumption. X and y are both even. Okay, x and y are both even. We'll play that game. What does that mean? Well, that must mean, x and y are both even and satisfy the equation, right? Okay, so if they're both even, they satisfy the equation. Then, okay, that means that this is them being even. This is them satisfying the equation. But that leads us to believe that an even number can be equal to an odd number. Left-hand side's an even number. Right-hand side's an odd number. That's not possible. An even number cannot be equal to... That's the contradiction right there. An even number cannot be equal to an odd number. There's your contradiction. Right? It's a statement that has to be false. A contradiction is a statement that is always false. So even number equals odd number, like 2 equals 3, is always false.
So I have a question.
Yeah.
So it's kind of related to how somebody just asked where the contradiction was. So you know how you let x and y both be even numbers?
Yeah.
And you let both of them not at least one. So when we're working with like contradiction, like if the question asks us, use contradiction, So do we, if it says at least one, do we use both? And if it says odd, do we use both as even? Like, I don't know if that makes sense.
Yeah. So like I just took the opposite of this, right? We take the opposite of what we need, right? So we need them like they're trying to prove that we're trying to prove that at least one of x and y is odd. Well, what I'm going to show is that the opposite of this leads to something that can never be true. The opposite can never be true. So if the opposite can't be true, then it must be true. So I take the opposite of this. At least one of x and y is odd. So they could be both odd. X could be odd. Y could be even. X could be even. Y could be odd. The opposite of this is that they're both even. Right? So this is what I suppose the opposite, the inverse of this for contradiction. It's really that starting line that's kind of the hardest part.
Okay, thank you.
No problem. In symbolic form, is it the same as for all x and y in z, if 3x plus then x and y is odd? Yeah. No. X, not x and y is odd. Then one of x and y is odd. Then x is odd, or y is odd, or both. They don't both have to be odd. It's just one of. Does that make sense, Jonathan? Yeah. Then x or y is odd. Yeah. Can you go over an example where we use a tautology to prove or disprove a statement? I don't know if I can think of an example where we use a tautology to prove or disprove a statement. Well, I mean, like so I'm thinking of like a predicate that's always true, right? And so by contradiction is essentially the same thing. We're proving you're trying to show that a fact is true, and the way you're doing it is you're showing that the negation is always false. Right? That the opposite of it is always false. It's never true that it's not true. So it must always be true. This is similar to what you're saying with tautology. You just take the negation of it one more time. Right? So yeah, I don't particularly know an example, but if you have one, I'll go through it. If you negate it, so someone just carrying on with some other comment that this person said, if you negate it, then it would be there exists an x and y in z such that if x and y is even, there exists an x and y in z such that if x and y, I forget exactly you'd have to, okay, this is what you should do if you want to take the inverse of it, because you have an implication. You got to turn the implication into like not P or Q, and then take the inverse of that and then switch it back to a implication. If you want. I can't do it in my head, but yeah, something along those lines. So for the negation. Okay, well it is 9:30, so I will wrap it up here. Unfortunately, there were a couple more questions, but I gotta get going. So that's our time for today. If you have any questions, feel free to email me. Now, will I be able to get back to everybody in time? I don't know about that. I'm also busy, but I will try my best, or I can direct you to the right places. Textbook's also great for this course. Otherwise, if you have any questions, I will stick around for a few minutes while I just upload the video and all that kind of stuff. Otherwise, good luck to everybody on the test. I hope it goes well. And maybe I'll see you for the final. If I do a tutorial for that. I do have content on YouTube for induction and the stuff after the midterm. So, because I taught this last year, I did tutorials last year. So yeah, that's it. No problem, guys. I hope you have a good night. Someone asked if I'm a TA. I'm not a TA, but next year I will be. Next year I'll be in the math program. So, but I'm not a TA. I just host tutorials. No problem, guys. Hope you have a good night. Good luck on the test.
Share, man. I still getting
Yeah, someone's saying, please do the final sesh for us. I ask Muse. Tell Muse if you want me to do the final sesh. Email Muse and say, could you please get Adam Sava to do the tutorial for that. And they will email me, and then I will do it. All right, guys. Yeah, you don't have to email. You don't have to, but if you really want to, by all means. I'm able to answer quick questions, but I do have to get going. So I'm not going to write anything else on the board here. But I can answer questions talking while I'm just closing the video here and all that.
Excuse me.
Yep.